Welcome to this complete guide on PyTorch TransformerDecoder. In this tutorial, we're going to thoroughly explore the TransformerDecoder architecture and understand how it differs from the TransformerEncoder we may already be familiar with. We'll master the cross-attention mechanism that allows the decoder to attend to encoder memory, build practical sequence-to-sequence examples, and visualize both self-attention and cross-attention patterns to really understand what's happening under the hood. Let's start by understanding the key differences between TransformerDecoder and TransformerEncoder. While they share many similarities, like both stacking multiple layers, typically 6 by default, both using multi-head self-attention, having feed-forward networks, and supporting optional final normalization, there are crucial differences that make the decoder special. The most important difference is that the decoder uses two types of attention. It has self-attention like the encoder, but also cross-attention to attend to the encoder's output. The decoder takes two inputs, the target sequence and memory from the encoder, while the encoder only takes a single source input. Decoders usually require causal masking to prevent looking ahead during generation, and they're specifically designed for sequence generation tasks, whereas encoders are more for feature extraction. The decoder requires memory input from an encoder, which the encoder itself doesn't need. Now let's set up our environment and import the necessary libraries. We're importing PyTorch and its neural network module, NumPy for numerical operations, and Matplotlib and Seaborn for creating beautiful visualizations. We're setting a nice visualization style, and importantly, we're setting random seeds to ensure our experiments are reproducible. Let's dive into our first example, the simplest possible transformer decoder. Here we're creating the simplest possible transformer decoder. We start by defining our key parameters. The D model is 512, which is our embedding dimension. We use 8 attention heads and stack 6 decoder layers. First, we create a single decoder layer with these parameters, then we stack multiple layers to create the full transformer decoder. Now here's the key difference from an encoder. We need two inputs: the target sequence, which is what the decoder is processing, and the memory, which is the output from an encoder. Notice how the target and memory can have different sequence lengths. The target is 20 positions long while the memory is only 10 positions long. This flexibility is crucial for tasks like translation where input and output lengths differ. After the forward pass, we verify that the output shape matches the target shape, which it does. Perfect. We can see the target decoder input has shape 20 by 2 by 512. The memory from the encoder has shape 10 by 2 by 512, and our decoder output maintains the target shape of 20 by 2 by 512. This shows that the decoder preserves the target sequence dimensions regardless of the memory size. Let me show you the parameter documentation for TransformerDecoder. The decoder layer parameter is required, and it's a single decoder layer instance that crucially has cross-attention capabilities. The num layers parameter specifies how many decoder layers to stack, just like in the encoder. And the norm parameter is an optional final normalization layer, also similar to the encoder. Now let's dive deeper into understanding cross-attention, which is what really sets the decoder apart. Here we're creating a custom decoder class to demonstrate cross-attention between the decoder and encoder. The decoder layer performs 3 key operations in sequence. First, it applies self-attention on the target sequence, allowing positions to attend to each other. Then it performs cross-attention between the target and memory, which lets the decoder attend to relevant parts of the encoder output. Finally, it passes everything through a feed-forward network. Notice how we're using different sequence lengths, 15 positions for the target and 10 for the memory. This demonstrates that cross-attention allows different input and output lengths, which is essential for many real-world applications. Excellent. We can see the target sequence has 15 positions, the memory has 10 positions, yet the output maintains the target shape of 15 by 4 by 256. This flexibility through cross-attention is what makes decoders perfect for sequence-to-sequence tasks where input and output lengths naturally differ. Now let's look at causal masking, which is absolutely critical for autoregressive generation. This is critical for understanding decoders. We're creating a causal mask that prevents the decoder from looking ahead during generation. Look at this mask structure. It's an upper triangular matrix filled with negative infinity values. Each row represents what a position can attend to. Position can only see itself. Position 1 can see positions 0 and 1, position 2 can see 0, 1, and 2, and so on. This ensures that when generating text or sequences autoregressively, each position can only use information from previous positions, not future ones. We apply this mask to the decoder, and it successfully processes the sequences while maintaining the autoregressive property. Perfect. We can see the causal mask structure clearly. The zeros allow attention and the negative infinity values block it, creating that distinctive triangular pattern. The decoder successfully processes an 8 by 2 by 512 tensor while ensuring proper autoregressive generation. This causal masking is what enables decoders to generate sequences one token at a time without cheating by looking at future tokens. Let's explore all the different types of masks that a decoder can use simultaneously. Here we're demonstrating how decoders can use multiple mask types simultaneously for complete control over attention. First, we have the target mask, which is our causal mask preventing future peeping. Then we have a memory mask that controls which source positions can be attended to. In this example, we're masking out the last two source positions. We also have target key padding masks for handling variable length sequences in a batch. Here we have sequences of length 10, 7, and 5 in our batch. Finally, we have memory key padding masks for variable length source sequences of 8, 6, and 4 tokens. The decoder applies all these masks together, giving us fine-grained control over exactly what each position can attend to in both the target and source sequences. All 4 mask types have been applied successfully. We have the causal mask at 10 by 10, controlling self-attention, the memory mask at 10 by 8 controlling cross-attention, and padding masks for both target and memory handling variable length sequences. This comprehensive masking system allows decoders to handle complex real-world scenarios with batched variable length sequences. Now let's build a practical sequence-to-sequence model to see how encoders and decoders work together. Here we're building a complete transformer for sequence-to-sequence tasks, like machine translation. The model has several key components. We start with separate embeddings for source and target vocabularies since they might be different languages. We add positional encodings to give the model information about token positions. The encoder processes the source sequence to create a memory representation. The decoder then uses this memory, along with the target sequence, to generate outputs. Notice how the encode method creates the memory representation, and the decode method uses both target and memory. The forward pass chains these together and projects the output to vocabulary logits for next token prediction. This architecture with 3 encoder and 3 decoder layers gives us a powerful but efficient model for sequence-to-sequence learning. Excellent! Our sequence-to-sequence model is working perfectly. We can see it's translating from a source sequence of length 15 to a target sequence of length 20, outputting logits for a 5,000-word vocabulary. The model has over 12 million parameters, giving it substantial capacity for learning complex sequence mappings. Let's implement autoregressive generation to see how decoders generate sequences step by step. Here we're implementing greedy decoding for autoregressive generation. The generate sequence function shows exactly how decoders generate text in practice. We start by encoding the source sequence to get the memory representation. Then we begin with just a start token. For each generation step, we create a causal mask for the current sequence length, decode using the generated tokens so far and the encoder memory, get the logits from the output projection, and greedily select the highest probability next token. We then append this token and repeat. This process continues until we reach the maximum length. This is exactly how models like machine translation systems generate their outputs one token at a time. Great, our generation is working. We can see the source has shape 10 by 2, and we've successfully generated sequences of length 15. The sample generated tokens show the model starting with token 1, our start token, then generating tokens like 2313, 3660, and so on. This demonstrates the autoregressive generation process, where each new token depends on all previous tokens. Now let's visualize the attention patterns in the decoder to really understand what's happening. Here we're creating synthetic attention patterns to visualize how decoder attention works. On the left, we see the decoder self-attention with its characteristic triangular causal pattern. Notice how each row, representing a query position, can only attend to positions up to and including itself. The later positions have more attention options, while early positions are limited. On the right, we see the cross-attention pattern between decoder queries and encoder keys. Unlike self-attention, cross-attention has no causal constraint. Each decoder position can attend to all encoder positions, allowing the model to gather information from the entire source sequence when generating each target token. The visualizations beautifully show the two types of attention in decoders. The self-attention heat map on the left clearly shows the causal triangular pattern in warm colors, where each position can only look backwards. The cross-attention heat map on the right shows full attention patterns in cool colors, where each target position can attend to any source position. This dual attention mechanism is what makes decoders so powerful for sequence generation tasks. Let's analyze how representations evolve through the decoder layers. Here we're implementing a layer-wise decoder to analyze how representations change as they flow through the network. We collect outputs from each layer to see how the model progressively refines its representations. Looking at the statistics, we can see that layer normalization is doing its job. The mean stays near 0, and standard deviation stays near 1 throughout the layers. The L2 norm stabilizes after the first layer, showing that the model maintains consistent representation magnitudes. This stability is crucial for training deep networks and shows that our decoder is well behaved. Perfect. We can see layer 0, our input, has a norm of 78.57 with slight variations in mean and standard deviation. As we go through layers 1 through 4, the representations stabilize beautifully. The mean becomes exactly 0 and standard deviation exactly 1, showing perfect normalization. The consistent norm values indicate stable gradient flow through the network. Let's visualize how these statistics evolve through the decoder layers to get a clearer picture. The visualizations show interesting patterns in how representations evolve. The L2 norm drops slightly from the input layer to layer 1, then remains perfectly stable through the remaining layers. The mean value quickly converges to 0, shown by the blue line approaching the red dashed baseline. The standard deviation similarly converges to exactly 1, indicated by the green line meeting the red dashed reference line. This stability is exactly what we want to see in a well-designed decoder, ensuring consistent and predictable behavior during both training and inference. Now let's explore common pitfalls and their solutions when working with decoders. Here's a critical pitfall that's easy to miss. When we run the decoder without a causal mask, the model can cheat by looking at future tokens. This completely breaks autoregressive generation because during inference, we won't have future tokens available. When we properly apply the causal mask, the model is forced to only use past information, which matches the generation scenario. The assertion confirms that the outputs are indeed different with and without the mask, showing the mask is having the intended effect. Always remember to use causal masks for generation tasks. Good, we've demonstrated the importance of causal masking. Without the mask, the model can incorrectly see future tokens, which would make it fail during actual generation. With the causal mask properly applied, we ensure correct autoregressive behavior where each position only sees the past. The outputs being different confirms the mask is working as intended. Let's look at another common pitfall involving mask dimensions. Here we're trying to use a memory mask with wrong dimensions. The memory mask should be target length by source length, but we're incorrectly using 5 by 5. This causes a runtime error because PyTorch expects the mask to match the attention matrix dimensions. When we fix this with the correct dimensions of 10 by 8, matching our target and source lengths, the decoder works perfectly. This is a common mistake when first working with decoders, so always double-check your mask dimensions. As expected, the wrong memory mask dimensions cause an error. The error message helpfully tells us the mask should be 10 by 8, not 5 by 5. With the correct memory mask shape matching target length 10 and source length 8, the decoder processes successfully and outputs the expected shape of 10 by 2 by 256. Let's compare the performance characteristics of encoders versus decoders. Here we're comparing the computational complexity of encoders and decoders with identical configurations. Both use 512-dimensional embeddings, 8 attention heads, and 6 layers. The parameter comparison shows that the decoder has about 25 million parameters compared to the encoder's 19 million, which is 33.4% more. This extra capacity comes from the additional cross-attention layers that decoders need. For memory complexity, we can see that decoders use approximately twice as much memory as encoders. This is because decoders compute both self-attention, which is O of target length squared, and cross-attention, which is O of target length times source length. These additional computations are what enable the decoder's powerful sequence generation capabilities. The comparison clearly shows the additional complexity of decoders. With over 25 million parameters versus the encoder's 19 million, decoders have 33.4% more parameters due to their cross-attention layers. Memory usage is doubled because decoders need to store both self-attention and cross-attention matrices. This extra complexity is the price we pay for the decoder's ability to perform conditional generation based on encoder outputs. Let me summarize the best practices for using TransformerDecoder. The key differences from encoders are that decoders require 2 input sources, target and memory. They have an additional cross-attention mechanism. Causal masking is essential for generation, and they have about 50% higher complexity. Use TransformerDecoder for tasks like machine translation, text generation with conditioning, any sequence-to-sequence mapping, and conditional generation tasks. Critical implementation tips include always using causal masks for generation, remembering that memory is required from an encoder, ensuring mask dimensions match correctly, considering manual layer initialization, and using padding masks for both target and memory when dealing with variable length sequences. Finally, let's build a complete simple translation model that puts everything together. This simple translator class shows a clean implementation of a full translation system. We use separate embeddings for source and target vocabularies, add learnable positional encodings, and use batch-first format for more intuitive tensor shapes. The encoder processes the source sequence to create memory, then the decoder uses this memory along with the target embeddings and a causal mask to generate outputs. Notice how we scale embeddings by the square root of D model, which helps with training stability. The model handles everything from embedding through encoding, decoding, and final projection to vocabulary logits. Perfect! Our translation model is ready for training. It successfully processes source sequences of shape 4 by 10 through the encoder to create memory, then uses the decoder with target sequences of shape 4 by 12 to produce output logits of shape 4 by 12 by 1000. With just over 4 million parameters, this is a compact but capable model that demonstrates all the key concepts we've learned about TransformerDecoder. You now have a complete understanding of how decoders work and how to use them effectively in your own projects.